Hello, welcome to Basics of Finite Element Analysis. Today is the beginning of the 5th week of this course, and this week we will continue our discussion on the finite element method in context of second order boundary value problems. And what we will be doing this week is essentially continuing our discussion on element level equations, and then we will use these element level equations to construct assembly level equations, impose the boundary conditions, and arrive at a reduced number of equations which could be solved to find out the values of deflections or the values of dependent variable at all the nodes in the problem. So, we will start this by having a very brief recap of what we did in the last lecture. So, the problem which we are trying to solve is represented by this governing differential equation d over dx a du over dx plus cu equals q, and this equation is valid when x is between the limits 0 to L, and let us say that we have two specific boundary conditions. The first boundary condition is u is at x is equal to 0 is 0, and the second boundary condition is that a times du over dx at x equals L is some constant, and let us call this q naught. So, what we had done was that we had constructed the weak form of this equation, but in finite element method we develop the weak form on an element by element basis, okay, and the weak form, the residual error and its weak form is equated to 0 on a element by element basis. So, if the limits, the boundaries of the element are designated as xa and xb, then the weak form is dw over dx a du over dx plus wc u, and then I am integrating it with respect to x, equals integrating it from xa to xb q times w dx and plus two boundary terms. So, the first boundary term is w, which is evaluated at xa, times qa, and the second boundary term is w, which is evaluated at xb, times qb. Okay. And we had defined qa equals minus du over dx times a, this entire thing, and it is evaluated at xa, and qb is, it does not have this negative sign. So, it is du over dx times a evaluated at xb. So, this is the weak form, and particularly, and it is the weak form at element level. So, then what we had done was we had developed relations for interpolation functions. We had developed two relations for psi 1 and psi 2 for a linear element, and we also had developed relations for a quadratic element. So, we assume at this stage that u for the eth element is equal to uj psi j, and I am summing it on j. So, that is my approximation for u, and I am assuming, because I am going to use Rayleigh-Ritz approach, that my weight function is same as psi I. So, I put these two relations back into the weak form, and what I get is this equation and the constants at node positions are uj's. So, I have put it here, and this equals, so that is the left side of the equation, and the right side is q and times w, which is psi I dx, plus I have these two boundary terms. So, I get psi I evaluated at x a times q a plus psi I evaluated at x b times q b, and the superscripts on all these guys is E, because this corresponds to eth element. And then we had from this relation expressed the same equation in matrix forms. So, this is my K matrix for the eth element multiplied by the vector for primary variable, which is u e, and this equals a force vector F e plus another force vector q e. And we had remarked earlier that in context of this particular differential equation, because we are using the weak formulation, our K matrix is symmetric. So, next what I will do is I will actually calculate the values of different K's, K11, K22, K21, K22, and also the values of F1 and F2. Okay. So, that is my overall equation, and we are going to integrate, we will conduct the integrations, and what we had discussed earlier was, in the last week was, so this integral is using the global coordinate system, because I am integrating from x is equal to x a to x is equal to x b. But typically when we go in and conduct integrations in finite element, we prefer to use local coordinate systems. So, this x a will be replaced by 0 and x b will be replaced by h e, which is the length of the element. Also we had said that x gets replaced by local coordinate, which is x bar. So, those are the transformations we will do, and we will, using those transformations, we will find out the members of K matrix. So, we are going to integrate using local coordinate systems. So, the transformations will be that dx is same as dx bar, okay, because all I am doing is I am just offsetting it, the coordinate system, by an amount x a transforms to 0, xb it transforms to he, and because of this reason d psi I for the eth element dx it transforms to d psi I for the eth element over dx bar. Okay. Now, in local coordinate system we know that psi 1 in local coordinate system is equal to 1 minus x bar over he, and so this is for the eth element, and psi 2 which is a function of x bar in local coordinate system is equal to x bar over he. So, my derivatives d psi 1 over d x bar equals minus 1 over he, and d psi 2 over d x bar equals 1 over he. Okay. Thus, k I j for the eth element is equal to, I have to integrate 0 to he a times minus 1 over he, which is okay. So, actually what I am doing is I am computing k 1 1. Okay. So, it is a times d psi 1 over dx times d psi 2 over dx, which is 1 over he, plus, so we see this relation here d psi 1 over dx times d psi 2 d psi 1 over dx times a plus, oh there should be a c here, c psi 1 is 1 minus, and again psi j is also psi 1. So, 1 minus x bar over he, and all this is going to be integrated with respect to x. Okay. So, this is k 1 1 and this should be a negative sign, because this is psi 1 prime and this is also psi 1 prime. So, if I do this mathematics, I get ae over he plus ce he over 3. And what is ce? It is the value of c on the eth element. Okay. Same thing for a. It is the value of a for the eth element. There is no reason to think that a is not changing with respect to x. So, the only thing here when we are doing the integration, we are assuming that a is constant over the length of the element, but in the next element it could be a different number. I do not even have to make that assumption if I know the how a varies as a function of x. If I know the value of a as a function of x, then I can integrate it, then this relation will become somewhat modified. But here I am assuming that a is constant on an element level basis, but between one element and another element it changes. So, that is why I put ae and ce. Similarly, I get k 1 to e. If I do the same process, my integrand is minus 1 over he times 1 over he, right, plus so yeah, so you have this is dx bar plus c times 1 minus x bar over he, and this will be x bar over he dx bar, and this comes to ae over he plus CE HE over 6, and there is a negative sign here. And when I do calculation for K22, I do all this thing, and the answer which I get is same as K11, which is AE over HE plus CE HE over 3. For the force vector F vector, this is the definition for the F vector. So, I have to integrate Q, the product of Q and psi I over the domain. So, F1E is equal to integral of Q times psi 1 dx bar 0 to HE, and if I do the math, what I get is QE HE over 2, and F2E is also QE HE over 2. And finally, we will compute these terms. Okay? We are going to compute these terms. So, this term I will call Q1. This will be associated with the first equation, and this will be Q2. This will be associated with the second equation, right? Because based on the value of I, that is my ith equation. So, when psi I equals psi 1, that is the value of Q in the first equation. When psi I equals psi 2, that is the value of Q in the second equation. So, when psi I equals psi 1, the value of psi I at x is equal to xa is 1. The value of psi 1 at the first node is 1, and at the second node it is 0. So, Q1 is, so this term is QA in the first equation, and this term in the first equation is 0. In the second equation, this term associated with QA is 0, and this term associated with the second equation is 1 or QB. So, Q1 is equal to QA and Q2 is equal to QB. So, at this stage, I write my overall element level equation. So, the equation is AE over HE 1 minus 1 minus 1 1 plus CE HE over 6 2 1 1 2, and these two matrices are added up and they are multiplied by the vector U1E U2E, and this equals the force vector QE HE over 2 1 1 plus Q1E and Q2E, where Q1E equals QA and Q2E equals QB. Okay. Now, this equation is for two noded linear element. So, if we had a quadratic element, I would have element like this. So, this is node 1, this is node 2, this is node 3, right? And if I assume that the node 2 is located at halfway mark over the length of the node, then my K matrix this is, actually I have to put a superscript, this is equal to AE over 3 HE 7 minus 8, 1, 16, minus 8, 16, minus 8, 1, minus 8, 7, plus CEHE over 30, and in the matrix I have 4, 2, minus 1, 2, 16, 2, minus 1, 2, 4. Further, my FE matrix or vector is equal to QEHE over 6, 1, 4, 1, and my Q matrix or Q vector is Q1E 0, Q, actually I will write to remove confusion, QA and QB. And at this stage I wanted to make two important comments. When you look at this force term, okay. So now what we are going to do is we are going to interpret the differential equation in context of a bar problem. So if I have a bar, right, its cross sectional area, so its cross, so what is A corresponds to E times its cross sectional area, this is my x coordinate, and U corresponds to displacement. So this is a bar either under tension or compression. So U corresponds to displacement, then and Q is some distributed load, external load Qx. So it is some distributed load per unit length, per unit length. It is distributed over the length of the bar. At some places it could be 0, at some places it could be non-zero, and it could vary as a function of x. So Q is the distributed load in the axial direction, and its unit is newtons per meter. Okay. So if I have and suppose over an element, suppose Q is constant, then the total force which is on the on that element will be QE times HE, right. So this, and if it is constant, and that is what we have assumed here. So half of that load is shared by node 1 and half of that load is shared by second node. Okay. So that is the meaning of this QE times HE over 2. This represents the total external load because of distributed load, Suppose I also had a point load at this point. Suppose there was a point load P, then that P I have not factored into it, because here all I am talking about is Q. Okay. So F1 and F2, they represent total loads, consequential loads at nodes 1 and node 2, which are due to the presence of distributed load intensity in the direction of the bar's axis. And if that intensity is constant over the length of the element, then half of that total load, the total load will be QE times HE, half of that will be taken by the first node, half of that will be taken by the second node. So it will be evenly divided. Second thing, so this is one important statement. The second thing is this Q2, Q2 is what? It is defined as A times du over dx at x is equal to b, x is equal to xb, right, or at the second node element, node of the element. Now du over dx, if u is displacement, then du over dx is strain, du over dx is strain, and when you multiply that strain by E, because A is E times A, so if you multiply that by E, E times strain is stress, and that times A is the force. So what that means is that suppose I have an element and I am exerting a point load. Q was distributed load, this is a point load, I am putting some external point load here, then that will be equal to A times du over dx at that particular location, x is equal to xb. Okay. So these terms QA and QB, they represent point load terms, whereas F1 and F2, they represent the loads at the two locations which is attributable to the distributed load. This is important to understand, because we will use this understanding when we are developing the assembly level equations. Okay. Now let us look at the quadratic element. So this is my quadratic element, and it has two nodes, node 1, node 2 and node 3, right. And suppose the distributed load on this is QE and this is, let us say, constant. Okay. Then what is the total distributed load on the length of the element? Total load. Total axial load will be QE times HE, will be QE times HE, right. 1/6 of that load. So look at it, 1/6 of that load, QE times HE divided by 6, is borne by the first node. It is not equally distributed. This is what mathematics is telling us. So 1/6 of that load is taken by node 1, 1/6 of that load is taken by node 3, and 2/3 of that load or 4/6 of that load is taken by node 2. So the distribution or the bearing of these loads over a quadratic element is not 1:1, it is 1:4:1. Okay. Similarly, for a cubic element, this distribution may be different. Okay. So that is the second thing. So that is second point. So if we have, if you take, so why am I saying that? So suppose you are using a FE software. If you are using an FE software and you want to apply some distributed load over an element, if the software does not automatically do all this mathematics, if it does not automatically do all this mathematics, then what you have to do is you have to distribute this load in the right proportion at different nodes. If it is linear element, then it is easy, you just divide it by 2. If it is quadratic element, then you have to distribute it in 1:4:1 proportion. Okay. Otherwise your answers will be wrong. And the last point, or the third point, is now we will again look at this Q vector. Okay. So when I have, so again, so when I am looking at an element in isolation, basically I have cut this element, right, and the force point load here will be QB, which will be A times du over dx. And why is this appearing? Because I have cut it. So when I take the free body diagram, that QB will appear, right. Similarly, there will be, if I take the free body diagram, there will be QA on this end, if this is point A and this is point B, but there will be no force at the middle point because of my free body considerations. Okay. There may be a load in the middle point only if I apply some external point load at the middle point, but how do we deal with that? We will talk about it later. But if there are no external loads and if I cut an element, what I will see is that there will be QA at one end and QB at other end. Okay. And these forces emerge because I have taken a body in equilibrium and cut it. So for the body to remain in equilibrium, these things have to show up. Okay. You can, so this is in context of the differential equation as we see it in context of an axial bar problem, but we can make similar conclusions for other types of problems, because this equation, it not only represents that bar thing, but also for heat transfer and all that, but we can make similar conclusions in context of the nature of the problem for other categories of problems as well. So, this concludes our discussion today, and we will contribute this discussion in the next class.